In exercise 4.3.3, we are given a constant theta is 4, and we are given a probability density distribution, P, and we have to determine values for t such that the moment generating function of this random variable, or the associated random variable, is finite. So it's smaller than infinity. And we also have to determine r, the adjustment coefficient. The key takeaway of this exercise is to interpret the math to find the correct answer. The key solving ingredient will be to basically to solve the adjustment coefficient equation combined with the interpretation of the math. Let's get down to it. First, we will find for which t this moment generating function is finite. Now notice that the probability density of an exponential random variable with parameter let's say e is exponential with some lambda, say, then the density is given by lambda e to the power minus lambda x. So P is a mixture, the P we are given right here. P is a mixture of exponential random variables with parameters 3 and 7. And therefore, the moment generating function will also be a mixture between the exponential MGFs, moment generating function. So we can look in the table A of Mart or actually compute it, but the moment generating function of, let me first write the one down for E. So for E, the moment generating function is given by lambda over lambda minus t. So this is if you have one exponential, and for our x, which is the mixture of two generating functions of exponentials, it will simply be 1/2 times the sum of these two, where lambda is now replaced by 3 and 7 respectively. And if you don't believe me that this is true, you can also just go the brute force way and compute it, because you can compute this definition. And using this, okay, well, it is positive, and you can compute it like using the probability density function right here. And then if you plug in P in this expression, you will obtain the same answer. Now the question is, when is mxt finite, smaller than infinity? Well, clearly t cannot be 3, and it cannot be 7, because otherwise one of these will blow up and it will become infinity. So it has to be not equal to 3 and not equal to 7, but also it cannot be negative, because the moment generating function is by definition it's positive. So this is never 0, or at least never negative. Therefore, t must be smaller than 3, and t must be smaller than 7, but of course this one covers the case. Alright, so this is the answer to the first part. Now to find r, right, so we also have to determine r, the adjustment coefficient. To find r, we need to solve So that's the key solving gradient. You have to solve the adjustment coefficient equation, and this is given by so capital R is the solution to this particular equation. 1 plus theta times mu1 r equal to mx of r. Right, so capital R has to solve this equation, where this mxr is what we just computed, so it's the moment generating function. Now if we plug in what we know, then we have two unknowns. So this one we just computed right here, right? So this is, we just plug in, instead of t we can plug in r in this expression, but we don't know the expectation yet. So this is the expectation of x, and we don't know it yet, so we have to compute it. Expectation of x, well, it's a mixture of two exponential distributions, and the exponential distributions are, so let me write it as follows. So it's equal to exponential with parameter 3 plus the expectation of the exponential with parameter 7. Right, this is just how this density function is defined right here. And these are equal to, well, it's just 1 over the rate, so this is equal to 1/3 plus 1/7, and doing some simple algebra, this will give you 5/21 by making the numerators equal. Now this is one way. One other way, if we had realized what we had done right here, this is the moment generating function, so we could have just taken the derivative with respect to t and plugged in 0. T is 0. This would have given us the same answer here for the expectation. In any case, we can now have all the ingredients to solve for r. So we plug in the values for this equation. We get so we plug in the first moment of mu we plug in mu1, the first moment of x. Then we multiply this by capital R, and we set this equal to the moment generating function, and that was equal to 1/2 times this expression, and then we plug in r for t, so it's 3/3 minus r plus 7/7 minus r. Now theta was given to us to be 0.4, so this is actually 1 plus 0.4, so that's 7/5. And if we multiply this both sides by 2 to get rid of this fraction, then we get 2 plus, and then working out this, so this 5 here cancels against that 5, so we have 7/21, which is 1/3, multiplied by 2, so that's 2/3 times r, and this equals to 3/3 minus r plus 7/7 minus r. Now this equation is a bit annoying because we have r in 3 places, in here, and in 2 different fractions. So the first thing is to rewrite the right hand side so that we have at least one fraction. Now doing that, we want to make the denominators equal, so we multiply them, but then we have to multiply this 3 by 7 minus r, and we have to multiply 7 by 3 minus r. Right, so this will give us the multiplication. Now then this equation becomes, so we can rewrite this equation as this times 3 minus r times 7 minus r equal to 3 times 7 minus r plus 7 times 3 minus r. Now from here on, it's just expanding brackets and swapping, which I will not do in this video because it's a bit of a hassle, but it will result in the following equation. So we will have that it's r times r squared minus 7r plus 6 equal to 0. Now we know that so we can solve this, either r is 0 or r squared minus 7r plus 6 equals 0. And this gives us r equals 1 or r equals 6. And we know that now we have to pick which one is correct. So which one, remember that r is the number that satisfies this equation. And if you plug in 0, well then many parts cancel to be 0. So definitely this will be 0. And then we will have that 1 equals e to the power 0, which is again 1, so this will be 1 as well. So of course 0 is always a solution. Now the other one, r is 1, is a possibility. So this is, let's say this is the trivial solution. Does not really count. Now which one is it, r is 1 or r is 6? But recall that in part A we answered the question of when is this moment generating function even finite, and we realized that it had to be below 3. So definitely this one does, r6 does not qualify, since mx of 6 diverges to infinity. So therefore r equals 1 must be the answer, and it's the only one that can be the correct solution.